Hey everybody, I'm going to go over Brown-Lemay-Burston, question 3.55, part B. And this is a little different than part A if you watched the part A or if you did part A, because in this case now we're adding an extra element. We have carbon and hydrogen, and now we're going to do oxygen. Okay, I feel it necessary to talk a little bit about this, is that anytime we do these elemental analysis problems, whether it's combustion analysis or even gravimetric analysis, the whole idea is that you can take this information and you're trying to isolate the elements into a separate compound that you can find the mass of. So if you do gravimetric analysis, let's say of a chloride, you react this typically with silver, and what you can do is you can get all the silver as a solid that precipitates, and then you can find the mass of this guy. And from here, all the chloride from this compound is in the silver, and so you can figure out how much chloride is here, and then you can figure out the percent of chloride in your original sample. So if we look at the setup here, we have the same idea. Menthol has carbon, hydrogen, and oxygen, so it's some carbon, it's some sort of hydrocarbon. Okay, and when we burn this, it reacts to form carbon dioxide and water. Okay, and so what we know is all the carbon that was in menthol went to carbon dioxide. So if we can get an accurate mass of that, we know how much carbon dioxide is in there. And then the other thing is if we know how much hydrogen is in here, we know how much if we know how much water we have, we can figure out how much hydrogen there is, because the hydrogen goes all the way to here. Now this last step here is finding out how much oxygen. But if we know how much carbon and how much hydrogen, then the rest must be oxygen, and we can go from there. So I actually really enjoy doing these sorts of combustion analysis problems, because it's like a puzzle to me, and once I figure it out, I'm like, yeah, it feels really good. Okay, so in order to do this, we first have to figure out what the percentage of carbon and the percentage of hydrogen is in carbon dioxide and water, respectively. So I'm going to do that math over here. I'm going to go CO2. There's one carbon. So for carbon, there's one carbon, and it weighs 12. So that's 12. And then for oxygen, there's two of them times 16. That equals 32. So 12 plus 32 is equal to 44. And so now to find the percent of carbon and carbon dioxide, we take the part that's carbon over the total, and we multiply that by 100. And when we do that, I put in my calculator, we get 12 divided by 44 times 100. And we get that this is 27.3% carbon. Now I'm going to do the same thing for hydrogen, okay, or for hydrogen in water, okay. Okay, so that's the percentages we're going to use. So now, based on how much carbon dioxide and how much water we have, we can now take and figure out how much carbon and hydrogen we have, respectively. So that's what I'm going to do next. Okay? So I'm going to take 0.2829 grams of carbon dioxide, and I'm going to multiply that by the decimal percent, 0.273. Because 27.3% of carbon dioxide is carbon, and I'm going to get 0.2829 times 0.273. I'm going to get that 0.0772 grams of carbon are in that sample. And now I'm going to do the same thing for the water. Okay, so now I know how many grams of carbon and grams of hydrogen there are. How do we determine how much oxygen there is? Well, the oxygen is what's left over. Okay, we know that the overall sample weighs 0.1005 grams, and we know how much carbon there is, how much hydrogen there is, so the remaining mass must be that of oxygen. So I'm going to take these two values, I'm going to add them up. So I'm going to go 0.0772 plus 0.0129, and I'm going to get that this is equal to 0.0901 grams. And now I know that 0.1005 grams of sample minus how much carbon and hydrogen there are is going to give us the leftover mass, 0.1005. Sometimes my fingers get ahead of my my talking. Minus 0.0901, and so that's 0.0104 grams of oxygen. So now we have the number of grams of carbon, the grams of hydrogen, and the grams of oxygen in this thing. Now we can go and do kind of a straightforward, normal percent composition problem where we do percent by mass. Okay, so I'm going to come down here, I'm going to say 0.0772 grams of carbon. I'm going to go down here and I'm going to go 0.0129 grams of hydrogen. And then I'm going to go here and I'm going to go 0.0104 grams of oxygen. Okay. Now, the steps are just like we've always done. We're going to take and we're going to divide by the molar mass. So I'm going to take this, I'm going to divide this by carbon's molar mass. So I get 0.0772 divided by 12.01. And I'm going to get 0.00643. Now I'm going to do the same thing with hydrogen and oxygen. Now that I have the moles, that's in essence what we're doing here. Okay. Now I'm going to do the next step, and the next step is finding the ratio. Okay. So I take each of these and divide by the smallest value. And no matter what we do here, there's always going to be a value that's 1, because we're going to compare all these numbers and find the smallest and divide each of the numbers, even the smallest one, by that. So this is 0.000650. We divide that, and we get that is equal to 1. We take these two and divide them by that, and we get okay. So now we have our ratio. Now the funny thing about this ratio is that when we go to the last step, which is your fiddle step to make it to make them whole numbers, it just seems weird. Okay, I don't know if you understand what I mean, but I don't know. So here's the thing: when we have a lot of these high numbers, and keep in mind this is experimental data, what we can do is we can kind of cheat the system. You ready for the system cheat? So here's what we're going to do by cheating the system. I'm going to read, and I'm going to know that the molar mass is 156 grams per mole, right? 156. So here's what I have already. I have that it's C 9.89, H 19.6901. So what I'm going to do is I'm going to take this formula, even with the funny decimals, okay, and I'm going to see what fraction or multiple of 156 it is, okay, because if it's, let's say we do this and it comes out to be 78, okay, if this comes out to be 78 when I find the mass of this, then I know I have to take that formula and multiply it by 2. Okay, because these fractions are so weird, or, you know, they're not obvious what we need to do. So I'm going to kind of game the system. So I'm going to find the molar mass as if this is what we have. Okay, so I'm going to go carbon. I have 9.89 of them times 12 the molar mass, plus I have 19.69 hydrogens times its molar mass, plus 1 oxygen times its molar mass. And you don't have to show that 1 times, but when I do that, I get a total of 154.6. Well, golly, that's almost equal to this. So what I know is experimentally, we don't have to multiply any of these numbers. We can just round them. So the formula for menthol here is simply C10H20O. Okay? And that checks out. Okay? So that's our formula for menthol, and I hope all of that made sense. Feel free to watch this again and keep working through the problem to make sure that you can do these sorts of things. Have a great day.